So we use number theory and modular arithmetic on the channel quite a bit. So I thought I'd make a little review video to fill in any of the details like it seems like are missing when we skip some steps. And mostly what we're going to do is look at when it's possible to solve the linear congruence ax congruent to b mod n for x. So we're solving that for x. So let's recall what congruence mod n is, or how it's defined. And this is maybe not a definition that you would see in a textbook, but this is equivalent to a definition that you would see in a textbook, and this is often given as an exercise. So we say that A is congruent to B mod n if they have the same remainder when dividing by n. So it goes back to division with remainder that you learned about in grade school. So let's look at some examples. So 7 divided by 3 is 2 remainder 1. I think it's pretty clear that the quotient is 2 and the remainder is 1. 34 divided by 3 is 11 remainder 1. Negative 8 divided by 3 is negative 3 remainder 1. And finally, 0 divided by 3 is 0 remainder 1. I should say that is 1 divided by 3. But that means that 7 is congruent to 34 mod 3. And they're both congruent to negative 8 mod 3. And then they're both congruent to 1 mod 3. And in fact, we would generally take this number 1 mod 3 as like the preferred number when we're working mod 3. And that's because it's between 0 and 2. It's on the list 0, 1, and 2. And those are their preferred remainders when you're dividing by the number 3. It doesn't really make sense to have a remainder of 7 when you divide by 3, because you might as well take the quotient to be larger. Now, kind of in a broader sense, if you take an even number and divide by 2, you get a remainder of 0. And if you take an odd number and divide by 2, you get a remainder of 1. That means that all even numbers are congruent to 0 mod 2, whereas all odd numbers are congruent to 1 mod 2. And that really means that you can think about congruence mod 3 as this 3-type generalization of evenness and oddness. So instead of having a choice between even and odd, you have a choice between these 3 things: 0 mod 3, 1 mod 3, and 2 mod 3. And more generally, when you divide by n, you've got a possible n remainders: 0, 1, 2, 3, up to n minus 1. So that's an n-type choice, kind of generalization of the 2 choice for evenness and oddness. Okay, so let's do a little bit of exploration to decide when it is possible to solve our congruence up here. And we'll do that by making a chart. So we're going to make a chart of multiples of x modulo 6 as x runs through all possible remainders. So let's start with 2x. So 2 times 0 is, well, that's obviously equal to 0. 2 times 1 is 2. 2 times 2 is 4. 2 times 3 is 6. But if you divide 6 by 6, you get a remainder of 0. So that's in fact equal to 0. 2 times 4 is 8. But if you divide 8 by 6, you get a remainder of 2. And then likewise, 2 times 5 is 10. That'll give you a remainder of 4 when divided by 6. So let's observe right here that we're only getting multiples of 2. And not only are they multiples of 2, but they're only between 0 and 5. So all multiples of 2 between 0 and 5. Now let's look at 3 times x. So here we'll get 0. Here we'll get 3. 3 times 2 is 6, but we discussed why that was 0. 3 times 3 is 9. Oh, but 9 is the same thing as 3 mod 6 because it's 3 more than a multiple of 6. 3 times 4 is 12, but that's 0 because that's a multiple of 6. 3 times 5 is 12, but that's 3. So now let's observe here, if we multiply by 3, we'll get multiples of 3. But when I say multiples of 3, I mean multiples of 3 between 0 and 5. So obviously you'll get multiples of 3 when multiplying by 3. But observe that you don't get maybe multiples of 3 outside a certain range when you're working mod 6. And then what about multiplying by 4? So you might say, well, we're just going to get multiples of 4, obviously, but this is where a little bit of simplification will change the answer a bit. Okay, so 4 times 0 is 0, 4 times 1 is 4, 4 times 2 is 8, but we already discussed that 8 was congruent to 2 mod 6. 4 times 3 is 12, but that's 0. 4 times 4 is 16, but let's see, 16 is 4 again. And then 4 times 5 is 20, but that's 2 again because it's 2 more than 18. So here we're getting multiples of 2. So multiples of 2 between 0 and 5. Now let's multiply by 5 and see what we get. So 5 times 0 is 0. 5 times 1 is 5. 5 times 2 is 10. But we already discussed that 10 was the same thing as 4. 5 times 3 is 15. But that's the same thing as 3 when you're working mod 6. 5 times 4 is 20. You divide 20 by 6, you get a quotient of 3 and a remainder of 2. 5 times 5 is 1 because it's 25, which is 1 more than 24, a multiple of 6. So notice here we're getting, well, all of the numbers between 0 and 5. So I'll just say multiples of 1. Okay, so, well, what's true about all of these? Well, how is 2 related to our number 6 and our number 4? Well, notice that 2 is the GCD of 6 and 4. And 2 is also the GCD of 2 and 6. And 3 is the GCD of 3 and 6. Whoa, and 1 is the GCD of 5 and 6. So what's really going on here is that we are getting multiples of the GCD of A and N between 0 and 5. Okay, so that gives us some sort of idea to when this is solvable. This is solvable when this number B is a multiple of the GCD of A and N. Okay, so let's get that statement on the board and then we'll prove it. So here's a carefully written statement based off of that exploration we just did. So the congruence AX congruent to B mod N has a solution if and only if B is a multiple of the GCD of A and N. Furthermore, if we have a solution, then in fact, well, it's possible to have more than one solution. There are exactly GCD of A and N solutions. Okay, so this is an if and only if statement. Let's observe that. That means that there are 2 directions to prove. So let's prove this forward direction first. So in other words, we can suppose we have a solution. Okay, so let's do that. So let's suppose we have some number x, which comes from 0, 1, 2, 3, all the way up to n minus 1. So those are the possible remainders when dividing by n. So those are the only numbers we need to work with, such that, well, our congruence is satisfied. So ax congruent to b modulo n. Okay, so we're assuming this left-hand side of the if and only if statement. Now we want to prove that b is a multiple of the GCD of A with N. Okay, but let's observe that AX congruent to B mod N means that N divides AX minus B. So that's equivalent to them having the same remainder. So what does that mean? So that means that we are able to find some integer that I'll call y satisfying the following condition. So we have ax is equal to b plus n times y. Okay, good. And then also, let's suppose that D is equal to the GCD of A with N. We're just giving that GCD a name for like ease of notation. Okay, but what does that mean? So if D is the GCD of A with N, that means we should be able to write A as D times K and N as D times L for some integers K and L. Well, that's really the definition of being a common divisor. Okay, nice. But now let's push these two expressions for A and N into our equation right here, which we built out of our congruence. Okay, so let's see where that leaves us. We'll have D times K times X is equal to B plus D times L times Y. But now rearranging things, we'll get B is equal to D times Ly minus Kx. Oh, but that means that D is a multiple of D. Oh, but D was equal to the GCD of A of N, and so that's exactly where we needed to end up for this forward direction. Now let's look at the reverse direction. Okay, so now starting with the reverse direction, it's gonna seem like we're working on a totally different problem, but that's because this first bit is generally given as a lemma or a previous result in a textbook. But I'd like to put this all together into one proof, so we won't do that. Okay, so let's consider the following set of natural numbers, which I'll call A. And so that's going to be everything of the form A times U plus N times V, where U and V range over all integers, and then we're going to intersect that with the set of natural numbers. And so here I'll use natural numbers to be positive integers. So that means 1, 2, 3, so on and so forth. Okay, great. And then let's observe that the number N is inside of A. And we could just achieve that by taking U to be equal to 0 and V to be equal to 1. And then, well, since we're talking about a congruence here, generally we take congruences mod N exactly when N is a natural number. So that means N is inside of this set by its construction and the natural numbers. Okay, so if N is inside of A, then that means that A is non-empty. Okay, but then now we've got a non-empty subset of the natural numbers. So look right here, we're saying that it's non-empty. And then here, we're saying that it's a subset of the natural numbers. But like I said, we've got a non-empty subset of the natural numbers. Every non-empty subset of the natural numbers has a smallest element. That's called the Archimedean principle. Okay, so let's take that smallest element to be this number D. So I'll say D is equal to the minimum of everything in A. And, well, if it's in A, then it has to be of this form. So that means it has to be achieved by, I'll just say X naught and Y naught in Z. So, well, what do I really mean by that? That means D is equal to A times X naught plus N times Y naught. That's what I mean by achieved by those two numbers. And now we're gonna do a little bit of a claim. And this claim is that D is a common divisor of A and N. So that means I'm going to show that D divides A and I'm going to show that D divides N. So recall that our goal is for D to be the greatest common divisor. I guess I didn't state that, but our goal is for D to be the greatest common divisor. So that means it has to be a common divisor to start with. And so we're only going to prove that D divides A because showing that D divides N is exactly the same, just with, things switched around a little bit, the names of the numbers switched around. Okay, so let's divide A by D with quotient and remainder. In other words, we're going to write A as d times q plus our number r, our remainder. And since we're dividing by d, that remainder can only take a certain number of values. And that is all the values between 0 and d minus 1. Those are the possible remainders when dividing by d. Okay, nice. And now what we'll do is take this expression that we have. That is, we're going to replace d in the second equation by its expression in the first equation. So we'll have a is equal to, so instead of d, I'll write ax naught plus ny naught times q plus r. And then the trick here is to solve for r. So we'll have r is equal to, let's see, there's a tricky way to write it. So it's going to be 1 minus q times x naught times a plus n times q times y naught. Okay, nice. And now we're essentially done once we make some observations. So let's note up here that since r is less than or equal to d minus 1 and d is the minimum of a, that tells us that r is not inside of a. It's impossible for r to be inside of a because it would be smaller than the smallest element, which is a clear contradiction. But now let's observe that r is equal to something times a plus something times n. So that means it's of the form to be inside of a. So if r is not equal to 0, then r is inside of a, which is a contradiction to this observation that we made above. So that means that it cannot not be equal to 0, so that means that r is equal to 0. But now if r is equal to 0, thinking about this equation up here that we've been using, we have a is equal to d times q, which is the same thing as saying that d divides a. Okay, so there we have it. D divides a, so a is a divisor of d. So d is a divisor of a, and then using a parallel argument, we'll see that d divides n. That means d is a common divisor. Now let's show it's the largest such common divisor. We just finished showing that d is a common divisor of a and n. Now we're going to show that it's the largest such common divisor. And we're going to do that by starting with another common divisor. So let's suppose c in the natural numbers is such that c divides a and c divides n. So in other words, we have c is also a common divisor. Okay, but what does that mean? That means that a is equal to c times t and n is equal to t times s. And this is for t and s inside of integers. But now what we'll do is take these two expressions, this expression for a and this expression for n, and we'll put it into our expression up here for d. Okay, so that'll give us d is equal to c times t times x naught plus c times s times y naught. But that's equal to c times tx naught plus sy naught. But this equation right here tells us that c divides d. But if c divides d, then c is less than or equal to d. So if we've got a common divisor, it's smaller than or equal to our number d that we found before, meaning that our number d that we found before is in fact a greatest common divisor. So let's get that tagged on here. So notice that d equals the GCD of a with n. Okay, so now since b is a multiple of d, remember, that's our assumption if we're working in this reverse direction, then that means we have b is equal to d times z, and that's for some integer z. Remember, our assumption was that b was a multiple of the greatest common divisor. That means it's a multiple of d in this language. Okay, good. And now let's set x equal to x naught times z, and we'll set y equal to y naught times z. But then that essentially has the effect of multiplying this equation up here by z. And that will leave us with the following expression. So we'll have d times z on the left-hand side, which is b. And then on the right-hand side, we'll have a times x naught times z, which is a times x. And then likewise, we'll have n times y. Okay, so now look at this equation. We have b equals ax plus ny. So now we're going to reduce everything modulo n. That means we're going to divide every term by n and keep the remainder. Oh, but that's going to turn this n times y into 0, because if we divide that by n and keep the remainder will be 0. But that gives us the congruence we want. We have ax congruent to b modulo n as needed. Okay, so there we have it. We just proved the if and only if statement. And now we're going to prove a portion of the number of solutions statement. Okay, so now let's suppose we've got our solution to our congruence, and now we're going to construct more solutions. So let's introduce the notation that we've been using, which is d is equal to the GCD of a with n, and suppose x, which is from that set that we had before, 0, 1 up to n minus 1, is our solution. So is such that ax congruent to b mod n. Okay, nice. And now let's set the following numbers, or define the following numbers. I'll say x naught is equal to x, x1 is equal to x plus n over d, x2 is equal to x plus 2 times n over d, all the way up to x sub d minus 1 is equal to x plus d minus 1 times n over d. Okay, so kind of more generally, we've got this format that x sub m is equal to x plus m times n over d. And here m comes from the set 0, 1, 2 up to d minus 1. And you might be worried right there because we're taking this quotient. How do we know we're still within the integers? But recall that d divides n by our assumption up here. So n over d is in fact definitely an integer. Okay, but now let's note that these are exactly d different solutions, or we haven't shown their solutions yet, d different numbers modulo n, and d is the GCD. So we want to show that they're all solutions. So let's look at a times x sub m, which is ax plus a over d times m times n. Okay, but now notice that a over d is an integer, so that makes this whole thing right here a multiple of n, because after doing a over d, we still have an integer, so we have an integer times n. So that means this whole thing is congruent to ax modulo n after reducing, but ax was congruent to b mod n. So what we've just shown is that these x sub m's are all solutions to our congruence. So what we've done is found d different solutions, or GCD of a and n solutions to the congruence. Now I'm going to skip showing that these are the only solutions, as it's a bit tricky, and then we're going to get on to some examples. Okay, so our first example is to solve the congruence 10x congruent to 6 mod 12. So let's notice that 6 is a multiple of 2, and 2 is the GCD of 10 and 12. So by our theorem over here, we have a solution. Furthermore, by the second part of our theorem, we have exactly 2 solutions. Now, since the number 12 is fairly small, we should really just be able to guess and check these solutions. And this is like something that you generally do for small modulus numbers. So let's see if we can guess and check them. So let's observe that 10 times 3, well, that's equal to 30, but 30 is equal to 6 plus 24. but I can write 24 as 2 times 12. Oh, but that's a multiple of 12, so this is all congruent to 6 modulo 12. So that means that x equals 3 is a solution. So let's see if we can find another one. So let's do 10 times 9, so that's 90, but that's equal to 6 plus 84, but 84 is equal to 7 times 12. That's a multiple of 12, making this whole thing congruent to 6 mod 12. So that means that 9 is also a solution. So putting this together, we have two solutions. We have x congruent to 3 and x congruent to 9 modulo 12 as our solutions. Okay, and we know those are the only solutions by the number of solutions part of our theorem. Okay, so let's do a bigger example. So for our next example, we're going to solve 555x congruent to 15 mod 5005. Now let's observe that we can do the factorization of the two numbers in question and quickly observe that their GCD is 5, meaning that there is a solution, and in fact there are 5 solutions. And now we're going to do a bit of a trick. And so I didn't spell out this trick before, so I think it's good to see now. So since we've got a GCD of 5 everywhere here, and this number is a multiple of the GCD, we can solve an equivalent, it's not quite an equivalent congruence, but a related congruence, and then boost those solutions to a solution to our congruence. And how do we get that related congruence? Well, we divide all parts of this by 5, by that GCD. So that'll give us a new congruence, 111x congruent to 3 modulo 1001. Okay, great. But now let's observe by some stuff that we did before, that's equivalent to solving the following Diophantine equation. 111x plus 1001y equals 3. Okay, nice. But then how do we do something like that? Well, we do something like that with the extended Euclidean algorithm. So I won't go over the extended Euclidean algorithm, but this is in fact an example of how it works. So we're going to start with the larger number, and we're going to divide it with remainder by the smaller number. So 1001 is equal to 111 times 9 plus 2. So there I divided 1001 by 111 with quotient and remainder techniques. But now this 111 is going to go over here and be the new thing that's being divided. And then this remainder will go over here and be the new thing that's divided by. So that's going to leave us with 111 is equal to 2 times 55. 2 times 55 is in fact equal to 110 plus 1. And then once we get to the number 1 here, we know that our next remainder will be 0, and that's in fact the GCD. So that's creating a solution to that GCD equation that we showed had to exist inside of the proof of our theorem. Okay, so next up what we're going to do is invert these two equations to solve for the remainder. So here we have 2 is equal to 1001 minus 111 times 9. And here we'll have 1 is equal to 111 minus 2 times 55. Okay, great. And now what we'll do is take this number 2 right here, which was one of the remainders, and exchange it for its expression over here on the right-hand side in the lower equation. So that gives us the following. We'll have 1 is equal to 111 minus 1001 minus 111 times 9, and then times 55. But then maybe moving everything around, and really the important thing here is to treat 111 and 1001 as variables, if you will. So that's going to give us the following equation. So we'll have 111 times 496, and then plus 1001 times -5 is equal to 1. But now observe up here that we were trying to work modulo 1001. So the trick here is to reduce this equation that we've just built modulo 1001. And that's going to give us 111 times 496 congruent to 1 modulo 1001. But we didn't want this to be solving for a 1 over here, mod 1001. We wanted a 3. So we can get that by multiplying this 1 right here by 3, and then this 496 by 3. So multiplying that 496 by 3 will give us 1,488. But if you reduce 1,488 mod 1001, you get the number 487. So this is congruent to 487 mod 10001. Okay, great. So that's going to give us this new equation, or congruence. We have 111 times 487 is congruent to 3 modulo 1001. Okay, but that means that this number right here could be taken to be our first solution. So if we simply multiply this 111 by 5, this 3 by 5, and this 1001 by 5, we'll see that 487 satisfies our original congruence. And then by the proof that we had for the number of solutions, we can construct the other solutions as follows. So all of our solutions will be of the form x equals our starter solution, which we talked about being 487, plus 1001 times m, where m comes from the set 0, 1, 2, 3, 4. So that m is this number n over d that we had before. Okay, but then calculating out all of those numbers, we get the following list. So x can be 487, 1,488, 2,489, 3,490, or 4,491 mod 5,005. So there we have it, our 5 incongruent solutions. And that's a good place to stop. Thanks for watching and sticking around until the end of the video. And since you're here, don't forget to gently press that like button, subscribe, ring the bell, and select all notifications to never miss a video. If you want to get your name in the credits like you see here, access the live seminar series, review videos before release, and more, go to patreon.com/michaelpennmath and become a Patreon member today. If you want full ad-free course content, subscribe to my second channel, Math Major. I've got courses on linear algebra, complex analysis, and proofwriting, among several others. And that's everything. Bye.